Hello, I'm Dr. Harper. This video is a homework Excel tutorial part B for business forecasting and operations management. So let's bring up the problem. Part B says Diane, Ed, Frank work for a company that contracts all their business at the beginning of each fiscal year, so the demand time series will be stationary within the year. Although their company has seen growth from year to year, problems with their forecast have been increasing every year over the past 4 years, beginning with year 1 in the table below. Glinda, head of the forecasting committee, has called a meeting to discuss the quarterly forecast for next year. Before the meeting, Glinda collected and distributed the following data of past sales and requested each member of the committee to analyze a time series and bring suggestions for the next year's quarterly season forecast to the meeting. Now, these numbers may not be the same as your numbers, but the process is the same. So let's solve this problem. Question 1. Diane reported using a random component to keep it simple and not to change the procedure of using a 3-point moving average over the previous years. And there's 2 very good reasons for using a moving average. It's simple, and it has been done in the past and has worked well in the past. Glinda reminds Diane that using a moving average that assumes only a random component results in only one forecast value, which would be for the first quarter of year 5. Diane agrees, but recalls that the forecast for quarter 1 of year 5 would be the forecasts for every quarter into the future until they observe more data throughout the year. And that one forecast, or that estimate, is an estimate of the stationary mean. Glinda then asked Diane for a forecast for quarters 1, 2, 3, 4 for year 5 based on a random component. And so there's our answers. So let's get these answers. Let's highlight this, Control Z, and let's bring up Excel. And so let's come down here a ways and let's paste it. And then let's enlarge this so we can see how to work the problem. There we go. Okay. First of all, with a moving average, with a window of 3, the moving average, you always use the last 3 values of the time series. Where the last 3 values of this time series are these 3 right here. So let me box that in. So therefore, the forecast here would be the average of these last 3 values, 1, 2, 3. And then that'll be the forecast for every time period in the future, because that is the estimate of the stationary mean, assuming a stationary component with just a random component. And therefore, it's going to be the forecast for every time period in the future. So that right there represents Diane. That's Diane's forecast. Okay? So there's the first one. Okay, now the second one. And we say 4250 was the answer. Ed argues that seasonal and random components should be considered, since seasonality in sales data is likely. And that's a very good reason to consider seasonality, because that's very true. Sales data it's very common to have a seasonal component within sales data. So Ed does have a very good point. Glinda asks Ed for his forecast for the next year, for year 5, for quarters 1, 2, 3, 4, based on a seasonal and random components. Okay, and there's Ed's answers. So let's bring Excel back. And now when we have a seasonal and random component, then what we want for the forecast is the average of each season. So we've already have the data block. So this would be the average of quarter 1, and come down, and this would be quarter 2, quarter 3, and quarter 4. And so this will turn out to be Ed's forecast. And so we can bring this down here, and we can see Ed's forecasts were indeed 54, 43.20, 25.20, and 21.60. So there's Ed. Frank proposed to investigate the possibility of random seasonal and linear trend components after looking at a plot of the data. Okay, good idea. You should always plot the data to see what the time series looks like. So when it's in this format, it's easy to plot the data. Just highlight it, come up to Insert, down here to Charts, and let's just plot the charts, and there we are. We see here year 1 is blue, year 2 is orange, year 3, and there's the 4 quarters, 1, 2, 3, 4. So we can see that the pattern repeats every year. It's the same pattern every year, therefore it's seasonal. And every year it keeps increasing, and that's the trend component. So I kind of agree with that. I mean, I kind of agree with Frank. After looking at a plot of the data, he proposes to investigate random seasonal and linear trend, because that's pretty much what I see too. Okay, so now that we have a trend, we still block the data, but this time we want the slope. Okay, now for the slope, we're going to regress the time series onto the years, okay, once we've blocked it, because we know within a quarter between the years, the difference is no longer random, the difference is a linear trend. So therefore, let's put the independent variables here, 1, 2, 3, 4. Now let's come down here and let's do the slope. The slope of the data, and here's the data, y variables, comma, the x variables, which is 1, 2, 3, 4. That's the independent variable in parentheses. Now we're going to get the slope all the way across for quarters 1, 2, 3, 4. But even though the blue will be moving, we want the red to be fixed. So we highlight the red, F4, the dollar sign in the column and row. Column is D, C and D, row C, and row is 4, 5, 6, 7. Then it'll be fixed. And so there's our slope. And so we copy that over. And now we take the average. Average of all of these seasonal trends, okay, and this represents the seasonally adjusted trend. Okay, well that's a slope, but that's also a trend. That's the trend component. The slope is a trend component. So that is the seasonally adjusted trend. These are the seasonal trends. That's the seasonally adjusted trend. So now to get the indexes, well, since we're already here, we really should go. Usually when you're there and you have all the data, it's usually to get more information than you need, because they may come back and ask for it. So to get the seasonal indexes, you simply take the seasonal trend divided by the seasonally adjusted trend in F4 to fix that, and you copy that every single time, and there's our seasonal indexes. Now they didn't ask for that in this question. In this question here, all they asked for from Frank is a forecast. But we should go ahead and get the data anyway. So now the forecast. Okay, well the forecast equals the intercept of your data, comma, the time period, F4 to freeze again, plus the slope, well, we have the slope right here, times the next year, which is 5. Okay, and so this would be the forecast for year 5. And we copy this over. And so we see here for the next year, the forecast for Frank is given by those 4 numbers. We come down here, we see what did Frank get? And there's where he got, sure enough, 9150, 7320, 4270, and 3660. And so yes, we got the same thing Frank did. So good job, Frank. Glenda questions Diane about her assumption. You based your forecast on a random component which implies a stationary time series. That's correct. If you use a window of 4, what would be the estimate of the stationary mean from your moving average? What estimate did Diane report using a moving average of 4? Okay, well notice what Diane did here is a moving average of 3, because that's what was used in the past. But then what Glenda is asking, what if it was a MA4? Is there a difference? Well, yeah, there's going to be a difference. So we do the average of all four, the last four, 1, 2, 3, 4. So we're averaging 4 instead of 3. It turns out to be 5,100 instead of 4,250, so it's larger. Well, the forecast for every time period still would be the 5,100, but that 5,100 is an estimate of the stationary mean. With a moving average of 3, the estimate is 4,250. With a moving average of 4, the estimate is 5,100. Okay. Now, what you could do is say, okay, what's the estimate averaging all the numbers? Okay, but they didn't ask for that. But if they did, then I would put it up here. I would say, what's the average of all the data? All 4 years of the data is 3,600. Interesting. Okay, so it's in here somewhere. 3,600 we see here. All the data is 36, somewhere in here, right in the middle of this. Okay, so 5,100 is what Diane would report. Glenda questions Ed about his assumption. If the time series has a seasonal component, then what are the seasonal indexes that correspond to your seasonal forecast? There it is. So a lot of times when they ask you for a forecast, they'll go deeper. They go, yeah, well, what about this? What about that? What about this? What about that? Okay, and there's a 1 in there that shouldn't be there. And so now let's bring this up. And we say, okay, well, we've already done that. We did that right here. We bring this down, and sure enough, it's 1.5, 1.2, 0.7, and 0.6. I had a 1 in there that shouldn't be there, so I went 1.5 as the answer. So there's the answer to the seasonal indexes. Okay, and so this is what part was this? Part B. I hope this helps. This is all I have for this video. Take care.